Welcome. In this session, we are going to look at finding limits of difference quotients. Recall when we did rates of change or slopes of tangents in the introduction, we came up with limits of the form f of x minus f of c over x minus c. So this is an example of a difference quotient. We did a couple of these. Now let's do another one, this time with a rational function. So we will do for the function 1 over x, f of x minus f of 2 over x minus 2, and then the limit as x approaches 2. When I do these limits, I prefer to simplify the difference quotient first, so I'm going to do that here. For the function 1 over x, f of x is 1 over x, f of 2 is 1 over 2, so I get 1 over x minus 1 over 2, the whole thing over the quantity x minus 2. To simplify the complex fraction, there are two ways you can proceed. You can either simplify the numerator and, if necessary, the denominator and then divide, or you can multiply by the least common denominator for the little fractions. I will do the latter. The little fractions are 1 over x and 1 over 2. The least common denominator is 2x. I multiply the numerator and denominator by 2x. I will distribute the 2x in the numerator. So I get 2x times 1 over x minus 2x times 1 over 2. I'm going to leave the denominator in factored form so I can reduce the big fraction eventually. In the numerator I have 2x times 1 over x. I can cancel the x's and I get 2. In the second term I have 2x times 1 over 2. I can cancel the 2's and I get x. So I get 2 minus x. And I need to reduce this, and to do that I need to note that 2 minus x is the negative of x minus 2. So I can cancel the x minus 2's. I'll have negative 1 over 2x. As x approaches 2, the denominator approaches 2 times 2, which is 4. This is non-zero. So the limit equals the value of the reduced fraction, negative 1 over 2 times 2, or negative 1 over 4. Eventually, we will want to do difference quotients all at once rather than one number at a time. So we want to do difference quotients using a parameter. There are two ways in which we can do that, which I will illustrate in the next two examples. We'll also extend our reach a little bit by allowing square roots. So let's do the difference quotient at x for the square root function. Since I want to do the difference quotient using x as my value, I have to use some other name for the variable. I'm going to use t. The difference quotient is then root t minus root x over t minus x. We'll find the limit as t approaches x. For this to be defined, first of all, x should be non-negative. But if x is 0 and I'm doing two-sided limits, I might be using numbers which are close to 0, which includes negative numbers. And I cannot do square roots of that. So for this limit to make sense, x must be positive. So that when t is close to x, t will also be positive. And the difference quotient will be defined. So we'll assume that x is positive. Now I need to reduce the difference quotient. I have square roots. If you have square roots and there is no obvious factorization, you can always try rationalizing the numerator or the denominator, wherever the square root is. In this example, the square root is in the numerator, so we will rationalize the numerator. The numerator is square root of t minus square root of x. Its conjugate will be square root of t plus square root of x. Change the sign of one of the square roots. So I multiply both up and down by the conjugate. In the numerator, I have root t minus root x times root t plus root x. If I multiply that out, or if I just use the formula of factorization formula, I see that it's root t quantity squared minus root x quantity squared, or t minus x. So now we can reduce this fraction by cancelling the t minus x's. I get 1 over root t plus root x. As t approaches x, square root of t will approach square root of x. And the denominator is not 0 because x is positive, so its square root is positive. Positive plus positive is positive. So we don't get 0 in the denominator, so limit equals the value, which is 1 over 2 radical x. For our third and last example for this session, we'll do a difference quotient for a quadratic. This time, I will do the difference quotient in the other form, f of x plus h minus f of x over h, and x plus h approaches x if h approaches 0. So we are doing the limit as h approaches 0. When you do difference quotients in this form, it takes a little bit more work to do the initial calculation, but finding the limit is a lot easier, in contrast to the last example where it was easy to write down the difference quotient, but finding the limit involved more algebra. When we do difference quotient in this form, I prefer to do this in 2 or 3 steps. First, we will calculate and simplify f of x plus h. Then we will simplify the difference quotient. Finally, we will do the limit. The template for f is 2 times the variable squared minus 3 times the variable plus 5. So f of x plus h is 2 times the quantity x plus h squared minus 3 times x plus h plus 5. Now I need to expand this. So we'll first multiply out x plus h quantity squared. You can either use the binomial square formula. So x plus h quantity squared is x squared plus 2 times x plus h times plus h squared. We'll also distribute the negative 3 in the second term. So that gives me 2 times the quantity x squared plus 2x plus h squared minus, if I distribute the negative 3, negative 3x minus 3h, and finally plus 5. And to finish this portion of calculation, I need to also distribute the 2. So altogether I get 2x squared plus 4xh plus 2h squared minus 3x minus 3h plus 5. Now we are going to do the difference quotient. F of x plus h, which we just calculated, minus f of x, which is all of this. Remember to use parentheses because the negative for minus f of x applies to all the terms in f of x. Now I'm going to distribute this negative and then combine like terms. I have 2x squared minus 2x squared, that's 0. And then minus 3x plus 3x, that's 0. And then 5 minus 5, that's 0. That leaves just 4xh plus 2h squared minus 3h after combining all the like terms. Now I can factor the h out of the numerator. So I have h times the quantity 4x plus 2h minus 3. And now I can reduce it by cancelling the h's. So I'm trying to find, as it turns out, limit of the simplified fraction, which is 4x plus 2h minus 3 as h approaches 0. Since the polynomial limit equals the value when h is 0, so just plug in 0 for h, which gives me 4x minus 3. So the limit is just 4x minus 3. This concludes our brief look at finding limits of difference quotients. We'll come back to this topic in chapter 11. I will stop here for this session. Goodbye for now.